Welcome to my channel. Today, we're going to explore the fascinating world of agentic AI systems, covering everything from the foundations of artificial intelligence to the cutting-edge agent architectures being used today. Let's start by understanding how we got here. Artificial intelligence isn't new. It began back in the 1940s with McCulloch and Pitts proposing the first mathematical model of biological neurons. In 1950, Alan Turing gave us the famous Turing test. The field was officially established at the Dartmouth workshop in 1956, but then came a long AI winter. The 1990s brought a machine learning renaissance, with Deep Blue defeating Kasparov in chess and Watson winning Jeopardy! The 2010s saw the deep learning boom, with AlexNet revolutionizing image recognition and AlphaGo defeating the world Go champion, proving that neural networks could master even the most complex games. Now, artificial intelligence rests on three fundamental pillars. First, we have algorithms, the mathematical models that map inputs to outputs. Second, there's data, the information used to train and tune these models. And third, compute, the processing power needed for both training and inference. What's remarkable about the generative AI era is how dramatically each of these pillars has scaled. In traditional machine learning, we talked about megabytes to gigabytes of data and millions of parameters. Today's foundation models are trained on the entire internet, terabytes to petabytes of data, with trillions of parameters. Training that once ran serially now runs massively in parallel thanks to the transformer architecture. When you supercharge data, algorithms, and compute all at the same time, you get what feels like magic. These foundational models can read, write, summarize, and hold conversations that genuinely make sense. They've democratized AI in ways we never imagined, from helping students with homework to assisting professionals across every industry. So, where do agents fit into this landscape? To understand that, we need to think about the spectrum of autonomy in AI systems. At one end, we have the basic large language model. It has agency only in its output, meaning it can generate varied and creative responses, but it's essentially a single call and response. Move up slightly, and we get chatbots, which are really just large language models running in a loop, maintaining a conversation. Then we have workflows, where we orchestrate the large language model within predefined steps, coding exactly what should happen and when. Here's where it gets interesting. Agents represent a significant leap. Unlike workflows, agents have dynamic control flow that the large language model determines at runtime. They can decide which tools to use, when to use them, and how to sequence their actions based on the task at hand. Deep agents take this further with the ability to spawn other agents, control browsers, access file systems, and operate with even greater independence. At the theoretical end of this spectrum sits artificial general intelligence, though experts still debate exactly what that means or whether it's achievable. As you move along this spectrum, you'll notice a key trade-off. System autonomy increases while human intervention decreases. The large language model makes more decisions and humans step back. Andrew Ng coined the term agentic systems as an umbrella term to acknowledge that there's some level of agency at every point along this continuum. And here's an important timestamp. 2025 has been widely called the year of agents. This is a rapidly evolving field. What we knew 6 months ago may already be outdated, and what we're learning today will continue to evolve. Keep that in mind as you explore this space.
So, what exactly is an AI agent? Let me give you a clear definition. A generative AI agent is a software entity designed to perceive its environment, make decisions, and take actions to achieve specific goals. At the heart of every agent is a large language model serving as its brain. This model handles reasoning, planning, and decision-making. The fundamental operation of an agent follows a simple but powerful loop: plan, act, and observe, then repeat. Here's how it works. A user provides some task or request to the agent. The agent invokes the large language model with the task and a system prompt that defines its behavior. The model analyzes the request and plans what needs to happen. It might determine that it needs to use a tool, perhaps calling an API, querying a database, or executing some code. The agent executes that tool call, which is the act phase. Then it observes the result and feeds that information back to the large language model. The model evaluates the outcome and decides what to do next. This cycle continues, looping through plan, act, and observe, until the task is complete and the agent returns a final response to the user. The key insight here is that the agent doesn't just make a single call to the model. It's an iterative process where the model acts as both a planner, deciding what to do next, and an observer, evaluating the results of its actions. This is what gives agents their power. They can adapt, recover from errors, try different approaches, and work through complex multi-step tasks that would be impossible with a single model invocation. Think of it like giving instructions to a capable assistant. You don't need to specify every tiny detail. You give them a goal, they figure out the steps, execute them, check the results, and keep going until the job is done.
Now, here's the key distinction that separates agents from workflows, and this is crucial to understand. When you build a workflow, you're writing code that specifies a predetermined sequence of steps. Step 1, get the input. Step 2, call this API. Step 3, process the data. Step 4, format the output. Step 5, return the result. Every path is coded in advance. You decide ahead of time exactly what happens and in what order. It's static, predictable, and deterministic. An agent operates fundamentally differently. Instead of following a fixed path, the large language model decides at runtime which tools to use and in what sequence. You give the agent a goal and a set of available tools, but you don't tell it exactly how to solve the problem. The model figures that out dynamically based on the task, the context, and the results it observes along the way. This is the key difference you need to remember. Agents have dynamic control flow devised by the large language model at runtime. Workflows have static, predefined, coded paths. Think of it like this. A workflow is like following a recipe step by step. An agent is like asking a chef to make you dinner. The chef knows the kitchen, knows the ingredients available, and figures out how to create something delicious without needing step-by-step instructions. This distinction has real implications. Workflows are more predictable and easier to debug because you know exactly what path they'll take. Agents are more flexible and can handle novel situations, but their behavior is harder to anticipate. Understanding when to use each approach is one of the most important decisions you'll make when building agentic systems.
Let's break down the core components that make up every AI agent. After reviewing numerous references in this field, 4 essential building blocks consistently appear. First and foremost is the large language model, which serves as the brain of the agent. This is the foundational model that handles reasoning, planning, and task decomposition. When you give the agent a complex task, the large language model breaks it down into manageable subtasks and figures out how to approach each one. The quality of your agent is fundamentally tied to the capabilities of the model you choose. Second is the system prompt. Think of this as the agent's identity card, its character DNA, its instruction manual. The system prompt defines who the agent is, what its purpose is, and how it should behave. A financial advisor agent might be instructed to be eloquent and professional. A medical assistant might be caring and empathetic. Beyond personality, the system prompt contains detailed instructions about what to do, what not to do, and how to handle specific situations. In production, these prompts can become quite lengthy and detailed. Third, agents need tools and actions. These are the functions, APIs, and capabilities that extend what the agent can actually do in the world. Without tools, the agent can only think and talk. With tools, it can retrieve data from databases, call external APIs, execute code, browse the web, and interact with file systems. Tools are what transform a conversational AI into a capable agent. Fourth, and finally, is memory.
Large language models are stateless by default. They don't remember previous conversations unless you explicitly provide that context. Memory systems give agents the ability to maintain continuity, remember user preferences, recall past interactions, and build up knowledge over time. This transforms a single-shot assistant into a persistent collaborator. Together, these four components, the large language model brain, system prompt identity, tools for action, and memory for continuity, form the complete picture of what makes an agent work.
Since the large language model is the brain of your agent, choosing the right model is critical. Let's walk through the key criteria you should consider. Task complexity is your starting point. If your agent handles simple, straightforward tasks, a smaller, faster model might be sufficient and more cost-effective. For complex reasoning, multi-step planning, or nuanced understanding, you'll want a more capable model. Match the model's power to the difficulty of what you're asking it to do. Reasoning capability matters enormously for agents. Not all large language models are trained with explicit reasoning capabilities. Models designed for agentic workloads, those that can think through problems step by step, plan ahead, and evaluate their own progress, will perform significantly better in agent applications. Context window size determines how much information your agent can consider at once. Agents often need to juggle conversation history, tool outputs, system instructions, and retrieved documents. A larger context window gives the model more room to work with, but also costs more and can be slower. Tool calling support is increasingly important. Some models have built-in function calling capabilities, meaning they're specifically trained to recognize when to use tools and how to format those calls properly. While you can work around this with prompting, native tool support makes development much smoother. Latency directly impacts user experience. In a production agent, the model is called multiple times in a loop. Even small latency differences compound quickly. If response time matters for your application, factor this into your model choice. Cost is always a consideration. These models typically charge per token, and agents use a lot of tokens as they loop through reasoning steps and tool calls. Understanding the pricing model and estimating your usage is essential for sustainable deployments. Finally, compliance and data privacy requirements might constrain your choices. Depending on your industry and data sensitivity, you may need to use specific providers, host models yourself, or ensure certain data handling guarantees are in place. Check out benchmarks and leaderboards specifically designed for agentic workloads. The Hugging Face Agent Leaderboard, for example, can help you compare how different models perform on agent-specific tasks.
Memory is what transforms a stateless language model into a persistent, capable agent. Let's understand the three types of memory in agentic systems. First, there's intrinsic memory. This is the knowledge encoded in the model's parameters during training. It's what the model knows about the world, language, and how to reason. This memory is stable and doesn't change unless you retrain the model. It's the foundation everything else builds upon. Second is short-term memory, which corresponds to the context window. Here's the critical insight. Large language models don't actually remember conversations. Every time you call the model, you're sending it a fresh context. To create the illusion of memory, we append previous conversation turns to the context window. So if you've had 5 exchanges with an agent, all 5 are sent along with your new message. The model reads through everything and generates a response that feels like it remembers. This works, but the context window is limited. As conversations grow, you have to make decisions about what to keep, what to summarize, and what to drop. This is called context management, and it's part art, part science. Third is long-term memory, which persists across sessions. This goes beyond the context window and into external storage, typically databases or vector stores. When a user returns after days or weeks, the agent can retrieve relevant information from long-term storage about that user's preferences, past issues, or previous interactions. The challenges here involve deciding what information is worth storing, how to index it for efficient retrieval, and how to surface the right context at the right time. Information flows naturally between these types of memory. User input enters short-term memory in the context window. As conversations grow and context fills up, important information gets persisted to long-term storage. When relevant, stored information gets retrieved back into the context window to inform current interactions. Context management is one of the most active areas of research in agentic systems. What information goes in, what stays, what gets summarized or compressed. Getting this right is critical to building agents that feel intelligent and helpful.
Tools are what transform a language model from a thinking machine to an acting machine. Let's understand why tools matter and how they work. Large language models have inherent limitations. They have a knowledge cutoff date, meaning they don't know anything that happened after their training was completed. Ask about today's weather, the current stock price, or recent news, and they simply don't have that information. They also have no access to real-time data, no way to check your calendar, no ability to look up your database, no connection to external systems. And by default, they're stateless, with no memory of previous conversations unless that's explicitly provided. Tools solve all of these limitations. By giving an agent access to APIs, it can fetch real-time data from any service. With custom functions, it can execute specific business logic you define. Database tools let it retrieve and store information. Browser tools enable web searches and navigation. Code execution tools let it run scripts to compute results or process data. File system access allows reading and writing files. The tool calling flow is elegant in its simplicity. The large language model reasons about what it needs to accomplish. It decides it needs to use a tool and generates a tool request with the appropriate parameters. The agent framework executes that tool and captures the result. That result is fed back to the model, which then incorporates it into its reasoning and decides what to do next. What's remarkable is how naturally this works. You don't need to write complex integration code. You define your tools with clear names and descriptions, and the model figures out when and how to use them. Of course, getting the tool descriptions right matters. Clear, unambiguous names and documentation help the model make correct tool choices. This is where the real power of agents emerges. A language model that can think and a set of tools that can act combine to create something far more capable than either alone.
When a single agent isn't enough, you might need multiple agents working together. Let's compare the two primary architectural patterns, supervisor and swarm. In the supervisor pattern, you have a hierarchical structure. One supervisor agent sits at the top, managing a team of specialized agents beneath it. When a task comes in, the supervisor decides which specialized agent should handle it, delegates the work, receives the result, and decides what happens next. The specialized agents don't communicate with each other directly. Everything flows up to the supervisor and back down. Think of it like a traditional management structure where team members report to a manager. The swarm pattern takes a different approach. All agents are peers and can communicate directly with each other. When one agent completes its part of a task, it can hand off directly to another agent without going through a central coordinator. Think of it like a self-organizing team where members collaborate directly. Each pattern has trade-offs. In experiments, the supervisor pattern might require around 16 total hops for a complex task, with 8,000 input tokens, because everything bounces up and down through the coordinator. The swarm pattern for the same task might need only 8 interactions with 2 direct handoffs, using around 5,000 tokens. Swarm is often more efficient for smaller teams with simpler tasks. But as complexity grows, the swarm pattern can become harder to debug because there are so many possible paths through the system. The supervisor pattern keeps things more predictable and traceable since all coordination happens in one place. Here's the practical advice. Start with a single agent. Only move to multi-agent architecture when the complexity genuinely demands it. The overhead of managing memory, context, and handoffs between agents is significant. If a single agent with the right tools can do the job, that's usually the better choice. Reserve multi-agent systems for tasks that are truly too complex for a single agent's context window or that require genuinely different specializations.
As agentic systems mature, standardization becomes increasingly important. Let's look at 3 emerging protocols that are shaping how agents interact with the world around them. The Model Context Protocol, or MCP, was introduced by Anthropic to standardize how agents connect to tools and data sources. Think of it as a universal adapter. Instead of building custom integrations for every tool or database, you build to the MCP standard, and your agent can plug into any MCP-compatible resource. Recently, Anthropic donated MCP to the Linux Foundation under a collaborative effort with OpenAI, which signals strong industry commitment to this standard. Agent-to-Agent, or A2A, is Google's protocol for enabling communication between different agents. As we build more complex systems with multiple agents, they need a standardized way to hand off tasks, share context, and collaborate. A2A defines how agents discover each other, negotiate capabilities, and exchange information. AUGI, or Agent User Interface, emerged from collaboration between Copilot Kit, Crew AI, and LangChain. It focuses on the human side of the equation, standardizing how agents interact with users. Consistent patterns for how agents present information, request approval, and handle user input improve the overall experience. Here's a helpful analogy. Think about USB and HDMI ports. Before these standards existed, every device had different connectors and you needed specific cables for everything. Once we standardized, you could plug any USB device into any USB port. The same principle applies here. With standardized agent interfaces, you can plug and play different components. A tool built for one agent works with another. An agent built by one team can communicate with agents built by others. The benefits are significant. Interoperability means you're not locked into specific vendors or frameworks. Plug and play means faster development, since you don't need to build everything from scratch. Reusability means that tools and capabilities built once can be used everywhere. This ecosystem approach will accelerate what's possible with agentic systems.
Evaluating agentic systems requires thinking at multiple levels. Let's break down how to assess each layer of the stack. At the large language model layer, you're evaluating the brain itself. Does it follow instructions correctly? Is it accurate in its reasoning? Is it consistent across similar queries? How often does it hallucinate or make things up? Are there safety concerns or toxic outputs? These fundamental model qualities form the foundation everything else builds on. At the agent layer, you're evaluating the system's behavior. Does it decompose complex tasks appropriately? Does it select the right tools for each situation? Is the execution efficient, or does it take unnecessary steps? When it retrieves information, is it relevant and accurate? Most importantly, does it actually complete the tasks you give it? At the application layer, you're evaluating the deployed product. What's the overall performance and reliability? What's the latency that users experience? What's the cost per task or interaction? What's the error rate in production? How does the user experience feel? For evaluation methods, you have 3 main approaches. Code-based evaluation is automated testing with predefined criteria. It's cheap, fast, and consistent, making it ideal when you have ground truth or can define clear success criteria. Large language model as judge uses one model to evaluate outputs from another. It's more scalable than human evaluation and can handle nuanced assessments, though it's not free of biases. Human evaluation brings in expert annotators to assess quality. It's the most accurate for subjective or nuanced judgments, but also the most expensive and time-consuming. Here's practical advice. If you know what the correct output should be, use code-based evaluation. It's more reliable and far cheaper. Reserve large language model and human evaluation for open-ended tasks where quality is subjective. And remember, evaluation is not one time. Build it into your development and deployment pipeline so you're continuously monitoring how your agents perform.
Let's be honest about the challenges facing agentic systems and then discuss best practices for building reliably. Hallucinations remain a concern. Models can and do make things up, stating incorrect information with confidence. Unpredictable cost estimation is tricky because agents loop, and you can't always predict how many iterations a task will require. Agents can get stuck in loops, repeatedly trying the same failing approach. Debugging is convoluted when you're tracing through multiple model calls, tool executions, and decision points. Evaluating open-ended outputs is genuinely hard since there's often no single right answer. And framework stability is a real consideration in this rapidly evolving space. So what are the best practices? Treat AI as a junior assistant. It's powerful and helpful, but not ready for unsupervised critical decisions. Start with read-only access to tools and systems. Let the agent observe and recommend before you give it permission to take action. Add human approval checkpoints for any critical or irreversible operations. Implement comprehensive logging so you can trace exactly what happened when things go wrong. Test extensively before deployment and set guardrails and limits to prevent runaway behavior. Looking ahead, the technology is improving rapidly. Every few months, models become more capable, more reliable, and more efficient. Standardized protocols are emerging, making it easier to build interoperable systems. New patterns are developing, like using agents as tools within larger systems, or agents that can spawn and coordinate other agents. Here's what doesn't change. Fundamentals matter. Understanding how these systems work, their capabilities and limitations, when to use them and when not to, these insights remain valuable even as the specific tooling evolves. Focus on building real business value, not just cool demos. The technology is maturing. Progress is rarely linear. We'll hit some walls, learn from them, and push forward. Build carefully, iterate fast, and stay engaged with this rapidly evolving field. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.